Um, you know that the pressure is equal to nRT over V. N over V is molarity. So molarity times RT. And so if we look at Kp, you know, Kp is going to equal Kc, you know, with the molarity, times RT to some kind of factor here, which we'll talk about, which we call delta N of gas, right? Delta N of gas, if the number of moles of gas do not change, then we could do this quite quickly. For example, if we look at, if AA is a gas plus BB is a gas, this goes to GG, which is a gas, plus HH, which is a gas. Let's say if the number of moles of gas don't change, then this is what we're going to see when we look at something like this. We're going to see that Kp is going to be the partial pressure of G raised to little g, partial pressure of H raised to little h, dot, dot, dot. Partial pressure A, partial pressure B, dot, dot, dot. And then we see that the partial pressure, well, the pressure is equal to the molarity times this factor RT. And so we just substitute that. The pressure of G is equal to the molarity of G. The molarity of G we just call the concentration of G, right? Okay, the concentration of G times RT, right? We have this, raised to the little g power. Okay, this is going to be times the concentration of H times the RT raised to the little h power divided by concentration of A, RT raised to the little a, concentration of B, RT raised to the little b. And then we can simplify this. You know, when we simplify this, we just factor out the RTs. And so we get the concentration of G raised to little g, H raised to little h. Yeah, and then this is going to be RT, you know, times RT to the little g, right? Times RT to the little h, right? Dot. And then A raised to little a, B raised to little b, times RT, little b, little a, sorry, RT, little b. And so if we have the same number of moles of gas in the numerator and the denominator, then the RTs all cancel each other out. But if they're different, then the RTs won't cancel each other out. And so this is why we have this other factor. This RT we can further simplify. This is going to be Kc, right, times RT. What we'll do is we'll just do this. RT to the G plus H, you know, plus dot, 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 whatever. All right. Divided by RT to the A plus B, dot, dot, dot. And then when we do this, we'll just bring this up and subtract this. And so we get this, Kc, you know, RT. This is going to be, right, G plus H plus dot, 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 minus A plus, yeah, B plus dot, dot, dot. All right, so this is the sum of the coefficients of the gases on the products minus the sum of the coefficients of the gases on the reactants. And we call that delta N of gas. Delta N of gas is just products minus reactants. So the easiest way to remember delta N of the gas is if you go from 2 to 3, that's plus 1 mole, so delta N is plus 1. If you go from 3 to 2, that's minus 1 mole, so delta N is minus 1. And so we just go and see how the number of moles of gas change.
Is this always true? Not KC that way?
Yeah. This is always true. So sometimes Kp and Kc will be the same. Sometimes they won't. You know? I don't know what I asked on the multiple choice question. Oh, Kelly?
Yeah. Okay. Are you deriving the relationship from KC to KP?
Yeah, but you know, this relationship between KP and KC, you don't have to memorize it. I'll just give it to you. I'll just write it like this. A lot of the equations I don't expect you to memorize because I mean, it's not a bad idea to memorize them because next time you see it, it'll be easier to remember. On standardized tests, they don't give you equations. You have to have them all memorized, usually. But this one, if you forget it, you can derive it. You know, that's one possibility. But you don't even have to derive it because I'll just give it to you. Standard equation.
Yeah. So for the simplifying assumption, can we say we get stuck and we forget how to do it? Can we just continue without it?
You can continue without it. You don't need to do it. Simplifying assumption is just introducing an error into your calculation anyway. So if you could solve it without using the simplifying assumption, that's better, actually.
Wait, but if successive approximations fail, then we have simplifying assumptions.
Successive approximations only fails. Well, actually, it never fails.
It'll always work as long as you take the time to do it, right?
Right. Successive approximations is fail-safe. You don't have to worry about that failing. It'll never fail.
How complicated
Simplifying assumption will fail at times, you know.
it's
Larger than 5% or if X drops out.
Are you going to ask us to do it on the test? Or
What's that?
are you going to ask us to do the simplifying assumption on the test?
It's very possible.
Or just find X?
You know, the situation is you're not allowed to use a programmable calculator. And so I get hit with this. You know, David, you're not the first person to ask this. You're the, I don't know, 100th or hundreds of them. Hundreds of people say, you know, why bother with a simplifying assumption? It just introduces an error and you don't need it, right? You don't need it for like 99.9% of the problems. But for 0.1% of the problems, you do need it. Otherwise, you aren't going to be able to solve it. And so, you know, try to solve. I don't know about the last test. Try to solve that problem without the simplifying assumption and see how far you get. Unless you already solved it. Did you already solve it? The one I posted on Piazza. No. Usually, you know, because the simplifying assumption is not needed for a lot. You know, you could. Some people are pretty good with algebra and they can manipulate things pretty fast. But the problem is you can avoid it. You know, you sacrifice one problem, it's okay, big deal. You sacrifice one problem, but if that problem is worth a good chunk of the test, then some points lost there. But that's just for this class. You know, as you go higher in science, you have to do assumptions. There's no way around it. You might as well do it now. Try to solve the problem. As I think back, I'm not sure if I made this one that way, but these little tricks I give you, you know, for most of the problems, you don't have to use them. It's just that one problem that you get hit with that you have to use all the tricks in the book. Otherwise, you can't solve it. And so sometimes I'll throw that problem out there on the test, you know, to see if you can do it. And so you don't have, of course you don't have to use it, but you know how to use it in case you get hit with that one problem. If I decide to throw it out at you, that if you don't reset, and if you don't use a simplifying assumption, you aren't going to get an answer. I have lots of blank pages to prove it. Lots of people don't come up with the answer to it. Well, anyway, and they aren't that hard once you do a few of them.
How do you reset it?
How do you reset it? You just shift all the atoms to one side or the other, you know, as much as you can based on limiting reagent. And so you reset it to the right or you reset it to the left. Assume 100% forward reaction, 100% reverse. Then you treat it just like a Chem 1/8 stoichiometry problem. You know, a lot of those Chem 1/8 stoichiometry, when they're done in moles, you can just do it in your head. You know, you don't have to do long, drawn-out dimensional analysis type calculation. Or the ice table. Ice table's very easy once it's in molarity or moles. Okay, other questions? So that's good. You guys are getting prepared for Thursday then. The test. Chapter 15. All right, if there are no other questions, we'll continue with the lab. What ion did we leave off with? Aluminum? Did we do aluminum?
Yeah, we did up
Yeah.
to,
Was it Red Lake?
we went to,
We're on calcium?
yeah, we're on
Okay,
calcium.
let's do calcium then. So if we take our original unknown, and the unknown contains calcium, we add HCl, we expect NR, no reaction. You know, calcium ions, they don't really care about H plus or chloride, for that matter. That's NR. And then in the next step with the ammonia, you know, so we take solution 1 and then add our ammonia. Is calcium hydroxide soluble or insoluble? Calcium hydroxide is, well, hydroxides are insoluble, except for, yeah, group 1, ammonium, and calcium, strontium, barium. So calcium hydroxide is actually soluble. So it doesn't matter if we add extra ammonia here. You know, we aren't going to worry about precipitating out. And so calcium 2 plus NH3 plus H2O liquid yields NR, because calcium hydroxide is soluble. Expect to have any precipitate. And so 3, we take solution number 2, and then we add the what to it?
Ammonium oxidant?
Oh, before that. Or actually, maybe we didn't do any before that, huh?
Just add 3 drops of the
Ammonium oxalate?
Yep.
All right, so here we add the ammonium oxalate, and we get a white precipitate. And so calcium's like oxalate to form calcium oxalate.
Kidney stones.
Yeah. Four. Okay, so you separate the calcium oxalate from everything else, and then what do you do to the calcium oxalate? You add the hydrochloric acid. And so we'll take our precipitate from 3 plus HCl, and we should get a CCS, a clear colorless. Calciums are colorless, chlorides are colorless, oxalates are colorless. And so the reaction here is a metathesis or an acid base. Calcium oxalate, 2 HCl's, and yield calcium chloride plus oxalic acid. The driving force for this would just be stronger to weaker acid.
I see.
Okay, then we're going to take solution 4 and then do what to solution 4? going to do the flame test. So if we take solution 4 and do the flame, in solution 4, all we should have is what? We should have oxalate, you know, actually oxalic acid, calcium chloride, potentially magnesium. If magnesium sunk through here, then magnesium is not going to color the flame. So the only thing, should there be any sodium here?
It just says that it will possibly precipitate, so that we have to test it, or we have to test it.
Oh, then that's important. We should factor that in. What should we do with the magnesium?
You do you test that acid solution for magnesium, doing the normal test you would for magnesium on that solution. So you like save a little bit of that solution for it, and then you do the magnesium test on that.
Okay.
Reading
All right. What we're going to get here with solution 4 in the flame is a short-lived brick red color to the flame. You know. Do you want to know what it looks like? If you want to know what it looks like, we have calcium chloride in the dropper bottles. You can just take some calcium chloride, put it in the flame, and see what it looks like, or what it's supposed to look like. Hopefully our calcium chloride has not been contaminated. You know, that's always a risk, contamination. It's always a risk. Contamination, some things are just contaminated naturally. For example, barium chloride. Barium chloride, you know, there's always white precipitate in our barium chloride. Do you know where it comes from?
CO2.
It comes from CO2 in air.
Ah!
You know, or barium hydroxide, you know. Yeah, actually barium hydroxide is the one I was looking for. Barium hydroxide plus CO2 yields barium carbonate in water. It's an acid-base, Lewis acid-base reaction. And so if you see a lot of white precipitate there, you just either decant it off or centrifuge it and decant it off. You know.
Ah! I get it.
Other things are just contaminated by, you know, students. So we got to watch out for that because that can lead to false positives. All right, so take a look. We have calcium over there, and this one, you know, if you just have a hint of sodium, it's going to drown out any red color. You know, just a tiny bit of sodium, and that just you can't even see any brick red. It's just going to be yellow, orange.
Uh-oh, Sandra. Do you see that?
Okay, what's next? This would be the positive test for calcium. Okay, then we have zinc. Let's follow zinc along the flow chart. So, if we have our unknown and it contains zinc, with HCl we should get no reaction. Zinc 2 plus will not precipitate out with chloride or react with hydrogen ions. Zinc metal will, you know, but not zinc ion. And then zinc 2 plus, you know, zinc 2 plus, is zinc hydroxide soluble or insoluble? Insoluble. Yeah. Zinc hydroxide is actually insoluble. And so actually this is not zinc. This should be solution 1 plus ammonia / ammonium yields NR. This is the case where we can't add too much ammonia, you know, because the way we're going to control this is by Le Chatelier's principle. And that is zinc 2 plus should precipitate out. And so zinc 2 plus 2 ammonias plus 2 waters is supposed to give us zinc hydroxide. plus 2 ammoniums. Does Zn2 plus form a complex with ammonia? Tetramine zinc 2 ion? Do you see tetramine zinc 2 ion in your flow chart? No? Okay. That's the other possibility that could happen, is it could form a complex, but I guess it doesn't. Does it? It forms a hydroxyl, but not an amine complex? Huh, I wonder why it doesn't form an amine complex. Yeah, so we're going to form a hydroxyl complex, but why not an amine complex? Why wouldn't it form an amine complex? Why do you think? You know, why it doesn't form an amine complex is a good question. You know, I don't know why it doesn't form an amine complex. It must have something to do with the, not with the coordination number. Zinc is 4-coordinate usually. So it should form a 4-coordinate. That's why I said tetramine zinc.
Maybe properties?
Yeah, it has to do with, you know, what's driving these reactions is. What kind of reaction is this? If zinc were to form the tetramine complex, what kind of reaction is that? Zn2 plus 4NH3 yields ZnNH3 4 2 plus. The question is, why doesn't that form? It forms a hydroxyl complex, tetrahydroxyl, but why doesn't it form an amine complex? No, in the hydroxyl complex, the charge on the zinc stays the same, 2 plus, because of the way we count it anyway. It must have something to do with what? David?
Because the hydroxyl is a better Lewis base.
Well, you know, better is all relative. It turns out that amines are better Lewis bases than hydroxyls for most metal ions. We'll see that in chapter 24 when we revisit it. But the answer I'm looking for is very broad, very general. How many valence electrons does Zn2 plus have? You need the periodic table? Take a look at the periodic table. How many valence electrons does Zn2 plus have? 8? Because, okay, this is D, it's D10, right? And so if it loses 2, then it's D8, so does it have 8 valence electrons? It has 0. Yeah, that's correct. It has 0 valence electrons. It's filled up. You guys recognize that these are called the pseudo group 2s, right? These are the pseudo group 1s. Zinc is always plus 2. Cadmium is always plus 2. The Zn2 plus is going to have the 3D10 configuration. Cadmium 2 plus is 3D10 as well. So zinc and cadmium never need Roman numerals because those are always plus 2. Same with silver. Silver never needs a Roman numeral because silver is always plus 1. Copper deviates though because of other reasons. Gold, mercury deviate too. But we call these the pseudo group 1 and pseudo group 2. They're like the alkali metals and the alkaline earths. The alkali metals have 1 valence electron, alkaline earths have 2. This group has 1 valence electron, this group has 2 valence electrons, right? This is a filled D subcell. So that doesn't have any valence electrons. It doesn't have any valence. What's going on with the bonding? If it doesn't have any valence electrons, how can it bond? How can zinc 2 plus form a bond if it doesn't have any valence electrons? Well, What kind of bond is formed?
Coordinated.
Which means what? Which means both electrons come from the ligand for the bond, so it doesn't need any valence electrons for the bond. Right. And not only that, the answer to the question I was asking is there a simple ranking system for Lewis bases? This is a question I've asked over and over again. Is there a simple ranking system for Lewis bases? No, ammonia is a good Lewis base, but why doesn't it attack zinc? In fact, when you go on, and when we go back to chapter 24, you'll see a ranking where ammonia is actually a stronger Lewis base than hydroxide. You know, for metals, alkaline metals. So it's weird, and yet it doesn't attack it. Yeah, it depends on the central atom, man. And we have to look at. Well, whenever we form a bond, what do we have to look at? In order to understand bonding completely, what do we need to know? No, I guess it hasn't clicked yet. Or maybe it's a word people try to avoid saying. Hmm? Orientation in space is part of it. I mean, orientation in space, what tells you the orientation in space? What tells you about the structure? MO theory, right? We need MO theory to understand the bonding here. So we got to look at, you know, how the atomic orbitals do the
Overlap.
not overlap, because that's valence bond. They don't overlap in the MO theory. You know what they do? In MO theory, they do an LCAO. What does LCAO stand for? Right, so we got to figure out how they do the linear combination. Is that a favorable linear combination or unfavorable? You know, that kind of stuff. You know, so this is why this is much more difficult than Bronsted. Bronsted so easy. Lewis is much more difficult. Some people have tried to simplify it, like there's a professor at UCSB who tried to simplify it. When he came up with his theory, you know, or his method, he wasn't at UCSB. He was, I think, at Michigan. But he called it HSAB. HSAB. Have you ever heard of that acronym? HSAB? Probably not, because it was on the PowerPoint on week 1, HSAB, and it was right at the bottom of the PowerPoint. Probably not a big deal. Something to skip over. But HSAB means, or stands for, hard, soft acid bases. And so that's why it's so complex. And so, you know, I don't know. It's got to be, why doesn't it form an amine complex? I thought it would, but it didn't. So it's got to do something with the bonding, right? And so we have to, and that's why it's so tricky, because, you know, it'd be nice to be able to easily predict it. Well, HSAB tries to make the predictions a lot easier, but HSAB, unfortunately, is beyond the scope of this class. Therefore, HSAB is not even on your radar. And in order to properly predict these things for Lewis acid bases, we aren't. You know what we're going to do? We're just going to look it up. Where are we going to look it up? Appendix D. And so there's some things that we should try to predict. Of course, like Bronsted acid, that's easy, you know, stronger acid to weaker. But Lewis, much more difficult. We aren't going to predict. We're just going to look it up. And so what's next? Well, actually, did I finish? I wasn't finished talking about it. I erased it, unfortunately. Gosh.
2NH3 plus 2H2O yields ZnOH2 plus 2NH4.
So we got to control the pH. And so this is what we're going to do. We're going to increase the ammonium concentration, which is going to shift this left and then prevent precipitation. And so it's just a Le Chatelier's type deal. Just a tiny bit of ammonium is enough to prevent it, because we need lots of ammonia to get zinc to precipitate out. And so Le Chatelier's shift to the left. Otherwise, if we let the ammonia concentration get too high, then we would have gotten white zinc hydroxide precipitate. You know, some people at the end of the analysis, they go on, I got nothing for zinc. Well, they probably lost it here. Yeah.
Wait, so they lost it and then to start over or what?
Yeah. Well, you know, for your known, you don't have to start over at the beginning, right? For your known, all you do is, let's say you know what mixture of ions you have. If you know what mixture of ions you have, then you can just grab some off the bottle and make up a little mixture to continue working on. And so you wouldn't have to start all the way at the beginning. If you're on your unknown, then a lot of people will go, oh, then I didn't have any zinc present to begin with, and then missed it.
Missed my glue.
Yeah, they miss it. All right, then what do we do with the zinc after this? So this was number 4, 3? 2? Okay, so number 3 is what? I'll take a look at the flow chart. I want you to follow along in the flow chart. Okay. Did you was how did we no, you're skipping steps though.
Yeah.
What step are you skipping? No. Yeah, so let's see. We add the chloride, we got rid of that. We add the ammonium, we get rid of the 3+ cations.
Yeah.
Then we add the NaOH to the precipitate over there. But did we add NaOH to this? We skipped the ammonium oxalate. We need the ammonium oxalate here. It's important, otherwise, so solution 2 plus ammonium oxalate yields what? Do you get a precipitate of zinc oxalate? Do we get a precipitate of zinc oxalate? Why not? Why don't we get a precipitate of zinc oxalate? We got a precipitate of calcium oxalate. Calcium is 2+, zinc is 2+. Why don't we get a zinc oxalate precipitate? Because of the activity? What kind of activity? You mean the activity series? Calcium is more reactive than zinc? But unfortunately, the activity series is for the metals. Yeah, the calcium is more reactive. Activity series is for redox reactions. This is not a redox reaction. This is a metathesis reaction. Because we aren't looking at this, what's a better reducing agent. We're looking at, calcium 2 plus and Zn 2 plus and reacting with oxalate. This one reacts with oxalate. Why doesn't this one? See, this is it. This is the natural progression of things. The natural progression of things is like this. First, you start off just learning these things. Hydroxides are all insoluble except for group 1, ammonium, calcium, strontium, barium. And then after you've seen that for hundreds of times, it's like, okay, I know that. It's drilled in my memory. Then you start thinking like this. You start thinking, why is it that magnesium hydroxide precipitates but calcium hydroxide does not? Why? Because that would be the next step, because you're so bored with the previous thing, just that memorization, right? And so the natural progression of things is like this. You start to wonder a little deeper about things, rather than just accept it. Well, it just is, right? That's what we do with Lewis. With Lewis, we just gotta, that's the way it is. And if you really want to get deeper into it, then you're really going to have to dig into MO and HSAB and that kind of stuff, LCAOs, right? But for things like the solubility rule, it's the same thing. Why isn't it? You start to wonder about those things as well.
Does do radon hydroxides as well?
Radon? Radon, well, two problems with radon. One, radon is a Nobel gas. And so chemically, they're very unreactive.
I did not mean radon.
Radium.
Oh, okay. Well, then there's only one problem with radium. Although radium's half-life is fairly long.
I know, right?
Radium is radioactive. And so it being radioactive, and it's alpha particle emitter, you can see it here, it has a half-life of 1,620 years. So it's pretty long-lived. The reason you aren't going to memorize radium is that, we aren't going to get to work with it.
We don't have lead seeds.
But you're right, would radium be soluble like calcium, strontium, barium? It probably should be. It should be soluble, because I think this must be due to a size issue, right? Magnesium ions are a lot smaller, and therefore they can form stronger ionic bonds. So that's why. In fact, you should know about beryllium. Beryllium should be the smallest of the 2 plus. So beryllium hydroxide should be insoluble too.
Should grab better. Is it?
It should even grab better. It should form an even tighter lattice. But fortunately, you guys aren't going to work with beryllium, because beryllium is extremely toxic. Beryllium is like magnesium. They used to use that as a metal in aerospace industry, right? Because it's lightweight and has a pretty good structural rigidity to it, whatever. Good strength. And so, beryllium. And so, a lot of machinists who are machining beryllium metal end up dying. In fact, all of them died, I think, pretty much, some kind of cancer. And it's because of the small size, high charge. It displaces magnesium and calcium from other proteins, enzymes, whatever in your body, and binds so tightly, right? It doesn't let go. And so this really disrupts your 2 plus. Magnesium and calcium are important.
So for the hydroxide one,
They still use beryllium, though. Let me just say, they use beryllium as X-ray windows, because it's a solid. What's a solid with the fewest number of electrons? What solid has the fewest number of electrons?
Boron?
Yeah, boron's a solid. Boron only has 3 electrons, but it isn't the fewest. What's a solid with the fewest number of electrons? Lithium?
We're not frozen.
Lithium is it. And so why do you want a solid with the fewest number of electrons? You want a solid with the fewest number of electrons to make X-ray windows. X-ray windows. And you want a solid with the most number of electrons to make X-ray shields. Why that? Because electrons absorb what? Electrons in atoms absorb,
Energy.
yeah, light, right? Electromagnetic radiation, light. Therefore, you want something to shield you from light, you better use something with a lot of electrons, like lead. But you go, lead, no, there's solids with even more electrons, like polonium or uranium.
Yeah, no.
Ah.
You're reflecting some and getting out.
Yeah, right. And so, yeah. So what happens is that things become radioactive after, right, lead. So you don't want to use. So lead is used as X-ray shields. Lithium should be used as X-ray windows, except that there's a problem with lithium, and it's too active. Lithium is the most active element, right, on the periodic table. It'd make a bad X-ray window because if you splash water on it, you're gonna, yeah, right. It's going to ignite and cause. Beryllium won't ignite if you spill water on it, fortunately. And so beryllium's used, except it's very toxic. So you have to be very careful with it. That's all.
When would you ever have to see into an X-ray? First, look at X-ray.
When? Oh,
When would you need an X-ray window?
lots of people need X-ray windows. You know, they have X-ray windows to probe. You know, there's X-ray spectroscopy where they shine X-rays on it to probe what's happening, and so they do that a lot in vacuum equipment. Yeah, which reminds me of a story. I probably told Chem 1A this story, but my friend, he works at JPL, and they had a surplus sale, so he bought a whole bunch of stuff, and he ran out of room to store it. So he asked me if I could store some high vacuum equipment for him just in my garage, right, in the garage. I asked him what it was, and he said, just, you know, this vacuum equipment looks like submarine stuff, you know, very thick-walled stainless steel. But one of the pieces is a beryllium window in there, you know, beryllium window for shining X-rays. I said, no, thank you.
Not in my house.
Yeah. This is no big deal as long as you don't.
Rub it,
Right.
touch it, do anything.
Right.
Sprinklers on.
To him, it was no big deal. To me, it was a big deal. But if it's no big deal to him, why doesn't he store it in his garage? That's what I never figured out. Yeah, I'll take his bicycle or whatever else nice stuff he has. But right, but that, no. And then I thought, what is he going to do with that? You know, set up his home lab? You know, yeah. You might be surprised. I was at an open house. I went through an open house, and this guy set up a home lab in his garage, complete with a hood, you know. And then I was looking at all the chemicals. This is in a nice, quiet neighborhood, and the hood's just exhausting. You can't even tell from the outside, but the hood's exhausting out, you know. And then I look at the chemical reagents that the guy had, and they're all nasty, like carcinogenic, mutagenic. You know, I didn't know, but I didn't want to stay there not too long. But
Home lab.
a home lab, you can have a home lab. There's certain restrictions you have to have. And lots of people do because they want to tinker around and stuff. But
They want to research
In minute
stuff.
amounts.
Yeah. Apparently, this.
Roommates are carcinogenic too.
Yeah, chromates and dichromates are chromium-6, the infamous chromium-6. There's that, what was that, the film? I never actually saw that film, Aaron Brockovich or something, but I just heard about it. About the chromium-6 in the water. Yeah. So, you know, if you drink this stuff, it's going to cause problems. Oh, anyway, let's go back to this. So, you know, why doesn't zinc 2+ form an oxalate? There's got to be reasons. We could look at it deeper, but it just doesn't. That's what's observed.
This stuff is interesting.
So we got no reaction. Okay, then 4 is what?
But it is soluble.
Is it soluble or is it insoluble?
It's insoluble.
Does it form an oxalate? Zinc oxalate solid, PPT? Take a look at the flow chart. The flow chart's going to just tell you. It should be on there. You're right. Why doesn't it form a PPT? Is this because we have to look at MO? To understand this better, why it doesn't form a PPT, what should we look at? Should we look at MO, LCAO, that kind of stuff?
HSAB.
HSAB? Is that what we should look at? The ammoniums are going to come off, right? And so we're just looking at oxalate. Is that what we should look at? Not really. We should look more towards lattice energies. Remember lattice energies in crystal structures? But yeah, we should look at lattice energies. It must form a weak lattice. That's it. Or, you know, the only exception is when you get to heavy metals. The heavy metals, the salts like silver chloride, silver bromide, silver iodide, those aren't so ionic. Those have a huge covalent. And when it's getting more covalent, then we should look at, you know, LCAOs, MO, you know, covalent bond formation. So. All right, so it's not soluble. What's next?
We gotta evaporate to remove NH4.
Okay, why are we heating it? So we're going to take solution 3 and then heat it. And then what? It fumes. Does it fume? Yeah. And so what's the reaction here? So we're getting rid of ammonium by heating. And so what forms? You'd think ammonia would form, right? But it depends on how hot we heat it, because ammonium could react, because ammonium's a, you know, they say, well, I just saw, you know, on TV, what did I see? Maybe it was on Yahoo or something. I saw, you know, 20 household chemicals that you should never mix together. Have you ever seen that? No, it popped up yesterday, and I thought, oh, maybe I'll click it, but I didn't. But I know 2 never to mix together. Never mix bleach and ammonia. Bleach is a powerful oxidizer. Ammonia is a powerful or decent reducer. You're going to get a redox reaction, right? The same thing. Ammonium is a reducer. You know. Yeah. You could make some nasty stuff. So don't do that. All right. What else? It just goes to ammonia. It's potential. It potentially could, but I think there's something else that it reacted with, isn't there? I don't think hydrogen gas. I mean, we could try to sit here and figure it out. You know, different things, what it could decompose into, but we don't, because it's written in your lab manual. Did you find the equation in your lab manual?
What else do we have? So
Yeah.
it has with potassium, oh, you get it.
With ammonium or with zinc?
With the zinc.
Okay, what does ammonium react with when we decompose it?
I think we're gonna add some concentrated nitric acid and some stuff.
Do we add some concentrated nitric acid
Eventually, actually.
before evaporation or after evaporation?
After.
We add it and then evaporate it again.
Okay, why don't we want ammonium present when we add nitric acid?
Because then you will get ammonium nitrate.
Well, if we just get ammonium nitrate, that's no big deal. Ammonium nitrate is just soluble.
Oh, that's.
Why do we have to get rid of the ammonium? Well, we don't want ammonium present when we add concentrated nitric acid because that could lead to trouble, because ammonium is a powerful or decent, ammonium is a decent reducer, and nitric acid is a very powerful, especially at 16 or 15
It's a high concentration.
molar. 15 molar nitric acid, you're asking for trouble if you mix a decent reducer in there. You're going to get a little, especially because this reaction will generate gas. You know, when people pour bleach and ammonia down the sink and then look at it, then they get a face full of bleach and ammonia and other toxic gases that are generated because a lot of heat and gas is produced, right? And they look in there. The gurgling. What's that gurgling sound? Boom. No, it's not funny, I know, but
It's probably on that list.
it's on the list of chemicals not to mix, so just watch out for that.
That's why we're getting rid of it.
Yeah, we got to get rid of the ammonia before adding nitric acid, because you're going to hear a gurgling sound, and it's going to pop out of that test tube, for sure.
It's gonna break everything.
Well, so how do we get rid of the ammonium? We just heat it, and the ammonium just goes off as ammonium.
No, first you gotta.
Do we mix it with anything? Or?
Yeah.
Because there's a problem. Ammonium aqueous, this is stabilized. Ammonium aqueous is stabilized by having water molecules surround it with a delta minus, and it's also stabilized because they're counter ions. Can we just, if somebody asks you just to come up with a beaker of ammonium ions only, I don't want any chlorides or any anions, is that possible? It's impossible, right? Because of charge. Space charge, you're going to generate a huge voltage. And so what, do we just vaporize these into the gaseous state and just have gaseous ammoniums without any anion? No, I don't think so either. How do we get rid of the ammonium?
But ammonia is gas.
Solution of acid, acidic versus the nitric acid.
Well, think about it. Maybe we do add nitric before, then that might get rid of the ammonium by oxidizing it.
That's not what this was.
Well, why don't you just take a look, because it's just finding the information in the lab manual.
It says carefully that the HNO3 heat again to encourage.
Yeah, you gotta add nitric acid.
We got to add the nitric acid. So what we're going to do is we're going to, hopefully we don't have that much ammonium in here. We should do this in the hood, of course,
Yes.
in case it starts to
Aim away.
fume away. But tell me what's going on here. What's the reaction?
That's the ammonia gas and hydrochloric acid.
Well,
What's going on there?
no, just. This particular reaction you don't have to figure out because they just tell you what it is. Can you find it? Can you just thumb through the lab manual and then just find the equation for the reaction that occurs? You found it?
Yeah.
All right, what is it?
It's the ammonia chloride solid and the ammonia nitrate solid. You gotta, you add the nitric acid, it'll dry and you evaporate.
Okay.
You know, when you add the nitric acid.
It's okay, just tell me. So, what do they have on the left?
Ammonium chloride, solid.
Heat it up to form ammonia gas.
To ammonia gas.
And hydrochloric acid.
So it's just
It becomes, yeah.
to
So like
ammonia gas and
decomposition.
hydrochloric acid.
All right. So this is how we're going to get rid of it. What we're going to do is we're going to decompose not the ammonium ions, we're going to decompose solid ammonium chloride. And so what we're going to do to solution 3 is we're going to take our ammonium and then we got to have chloride. Where does the chloride come from? Are we adding HCl to this?
We added HCl.
At the very beginning from step 1? Okay, so there's going to be chloride left over all the way from step 1. Why would it be solid? Well, when we heat this up, we're going to evaporate all the water to get solid ammonium chloride. Here. Once, you know, ammonium and chloride, they don't normally precipitate until all the water is gone, and then they'll precipitate out, because there's no other thing left to do. And so once all that's gone, then we're going to continue heating this, and then we can decompose this. When we decompose this, this is going to form NH3 gas plus HCl gas. Now we aren't creating any just ions. This is all electrically balanced, so we're good. Are we adding the nitric acid before this or after this? We add the nitric acid and then evaporate it?
You evaporate and then you add the nitric.
Okay, that's very important. Why? Because the whole reason for getting rid of the ammonium is to avoid the reaction with nitric acid, I think. All right, once we get rid of all the reducer out of there, now we can add our oxidizer. But is the purpose of the nitric acid to oxidize something? And so then what we're going to do is we're going to take our residue, because there should be other ions present here, such as zinc 2+, right? Which is still floating around. And so the zinc 2+, hopefully there's enough chlorides present. The oxalate's probably going to decompose depending on how hot we heat it to CO2. And so we got zinc chloride, this is going to go to zinc chloride solid. But with the heat here, this amount of heat's not enough to decompose the zinc chloride. So we get NR. Zinc chloride shouldn't decompose here. And so our zinc should still be left in that solid residue sitting at the bottom of the evaporating dish. And so what we're going to do is we're going to take our solid, you know, whatever, PPT from 4, and do what? Add the nitric. This is an example of metathesis reaction here, except the driving force is just losing all the water. We evaporate all the water. So there's no other choice but to precipitate. And now we're going to add the nitric acid. Is it safe now to add the nitric? Yeah, it should be safe. I mean, nitric shouldn't really oxidize chloride ion to chlorine. So it should be okay. Unless the conditions are quite vigorous. So we take precipitate from 4, add nitric, what should happen? We should get, just a solution, a CCS, right? And so in other words, is the nitric acid really reacting? What's it reacting with? It's not reacting with anything. It's just water. We could just add water and dissolve it, right? but we'll need the nitric acid for later. So what's the next step after this?
That's an HCl.
Add some HCl?
I think it's the,
It says heat again until no more fumes are observed. Dissolve residue in 6 millimeters.
Yeah, I don't know if that means add the nitric acid like dryness or just
Just to no more fumes.
All right, add the nitric acid and then heat it.
yeah,
All right.
to remove the NH4.
heat until no fumes are observed, then you dissolve the residue in hydrochloric acid.
The residue with hydrochloric acid. All right, then something's missing here.
Well, after the, you add the acid. You can see the fume.
So, do we take solution 3, heat it, and then heat it to dryness, and then add the nitric acid? Yes?
Mm-hmm.
Okay. And then we take solution, the residue from this, which we'll call 5, in other words, the precipitate, and then add the nitric acid to this?
Yes. 16 millimeters.
And then heat it?
Heat again.
Heat it again?
Until
Okay.
there's no fumes observed.
Until no fumes. Okay. So we're going to observe fumes. And so what's happening here?
That is
Same question as earlier.
that is the ammonium nitrate solid producing dinitrogen dioxide.
Okay. So this one is, they're saying that there's some more ammonium left?
Yeah, because it binds with the nitrate from the nitric acid.
All right. And so ammoniums plus nitrate is going to yield ammonium nitrate, solid. Ammonium nitrate, solid. Have you heard of that before?
Gunpowder.
Yeah.
Fertilizer.
Fertilizer. Have you heard of
Good old fertilizer.
Have you ever heard of a place in Texas?
Oh, the factory that blew up was a ammonium nitrate.
It wasn't a factory.
Storage?
Fertilizer?
Yeah. I do remember a huge
Did I show this?
catastrophic explosion.
I didn't show this? I never did. Then I need to show you. Do you know what the worst industrial accident in the U.S.
In the
was?
U.S.?
In the U.S.? The worst industrial accident in the U.S. occurred in Texas City. Is it Texas City?
The one in China was
Oh, the one in China is way worse.
Always.
That one was unbelievable. You know what that was, though?
One guy stopped.
There was ammonium nitrate there, too. In fact, I should show that.
You're talking about the fireworks factory that went up, right?
Not the fireworks factory. I'm talking about the storage dock. Oh, my. You would have thought that was nuclear from the size of that explosion. Like there's, yeah, it was.
Satellite?
You should take a look at it. Well, let's see this one, because if you haven't seen this, then you should know that. You should know Texas City.
That's why we're doing this reaction in the hood.
Yeah, but
Meaning an explosion theory.
we do. If you see Texas City, I don't know if you really want to do this reaction. 5. You can opt out of this, or have your partner do it.
You're the EMT.
Yeah. No, that's scene safety. That's not the one.
Oh no, then they can go to the hospital.
Yeah, great.
That's what you have to do.
You can sew fingers back on them.
Because if on there you come out,
We were just talking about trying to do this. You know what's weird is it's the nitrate part of it, because you could use potassium nitrate, ammonium nitrate, and then there's like 6 different nitrates you could use to create that.
I think this is it. No, sorry, that's not it.
47.
No, that's not the video I wanted.
That's bad. That means that it's happened before.
it keeps happening the same spot.
Was it that long ago?
Yeah. Let me see if this is it. No.
I can see Texas Explosion 2 right there on the right. Yeah.
What's the video
I'm
called?
gonna come back and check out biggest explosion
That is
compilation.
enough.
Did you see that?
Shoot.
Biggest explosion compilation.
That's
What do
what
you
they
think?
had. Yeah, they had the biggest explosion compilation.
How about the explosion? The very last one.
How about put industrial disaster or something?
Don't tell me it's gone.
Right there. Oh, dude.
The bathroom always so cold.
All right, let's take a break here, and then I'll bring this up, and then we'll finish this really quick.